Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Seasons. An astronomical perspective on Earth's climate rhythms. In the vastness of the cosmos, our home planet Earth engages in a complex and beautiful dance, its movements and positioning giving rise to the seasons that define the cycles of life. Understanding the seasons from an astronomical perspective requires delving into the intricate interplay between Earth and its celestial environment, particularly the Sun. At the heart of this phenomenon is the Earth's axial tilt. The Earth's axis is tilted at an angle of approximately 23.5 degrees relative to its orbital plane, also known as the ecliptic plane. This tilt is the primary reason we experience seasons. As the Earth orbits the Sun, different regions of the planet receive varying amounts of sunlight at different times of the year. During the course of a year, the northern and southern hemispheres take turns being tilted towards and away from the Sun. This axial tilt means that the angle at which sunlight hits the Earth changes over the course of a year, leading to the variations in temperature and day length that characterize the seasons. When the northern hemisphere is tilted towards the Sun, it experiences summer, while the southern hemisphere simultaneously undergoes winter, and vice versa. This axial tilt creates the solstices and equinoxes, key markers in the Earth's annual journey around the Sun. The summer solstice, which occurs around June 21st in the northern hemisphere, marks the longest day and the shortest night of the year. This is when the North Pole is tilted closest to the Sun, and the Sun appears at its highest point in the sky at noon. Conversely, the winter solstice around December 21st marks the shortest day and the longest night, when the North Pole is tilted furthest from the Sun, and the Sun reaches its lowest point in the sky at noon. The equinoxes, occurring around March 21st and September 21st, are the moments when the tilt of the Earth's axis is such that the Sun is directly above the equator. On these days, day and night are approximately equal in length. The vernal equinox in March heralds the beginning of spring in the northern hemisphere, while the autumnal equinox in September signals the start of fall. One might ask, how does this axial tilt come to be, and why does it matter so profoundly? The Earth's axial tilt is thought to have been caused by a colossal impact event early in its history. A Mars-sized body, often referred to as Theia, collided with the proto-Earth, and this impact not only created the Moon but also set Earth's axis at its characteristic tilt. This tilt has been relatively stable over geological timescales due to the gravitational influence of the Moon, which stabilizes the Earth's rotation and prevents extreme variations. In a world without this axial tilt, the Sun would always be directly over the equator, and there would be no significant seasonal changes. The result would be a planet where the climate would be largely dictated by latitude alone, with the equator perpetually hot and the poles eternally cold. The seasonal rhythms we know today would not exist, drastically altering the planet's ecological and climatic systems. The variation in the angle of sunlight is what causes the differences in temperature that characterize our seasons. When the Sun is higher in the sky, its rays hit the Earth more directly and are spread over a smaller surface area, making the energy more concentrated and the temperatures warmer. When the Sun is lower in the sky, its rays hit the Earth at a more oblique angle, spreading the energy over a larger area and thus providing less warmth. However, the story of seasons is not solely about sunlight and angles. The Earth's orbit around the Sun is not a perfect circle but an ellipse. This elliptical orbit means that the distance between the Earth and the Sun changes over the course of a year. The Earth is closest to the Sun, a point known as perihelion, in early January, and farthest from the Sun, known as aphelion, in early July. One might think that the varying distance from the Sun would have a significant impact on the seasons, but this effect is relatively minor compared to the influence of the axial tilt. The difference in solar energy received by the Earth due to this variation in distance is about 7%, which is much less significant than the changes brought about by the axial tilt. The impact of the Earth's elliptical orbit does subtly modulate the severity of seasons. For instance, because the Earth is closer to the Sun during the southern hemisphere's summer, this hemisphere experiences slightly warmer summers and cooler winters than the northern hemisphere, which is farther from the Sun during its summer. The interplay of these astronomical factors results in the diverse and dynamic climatic patterns we observe on Earth. Seasonal changes affect every aspect of life on our planet, from the growth cycles of plants to the migration patterns of animals, and even human activities. In addition to the axial tilt and orbital eccentricity, other factors also play a role in shaping the Earth's climate and seasons. The distribution of continents and oceans, the presence of mountain ranges, and the composition of the atmosphere all influence how heat is distributed and retained on the planet's surface. For example, the specific heat capacity of water means that oceans heat up and cool down more slowly than land, leading to milder temperatures along coastlines and more extreme temperatures inland. The Earth's climate system is also influenced by its rotation. The Coriolis effect, a result of the Earth's rotation, causes moving air and water to turn and twist in predictable patterns, creating the prevailing wind patterns and ocean currents that help distribute heat around the planet. Seasonal changes also drive complex feedback mechanisms within the Earth's climate system. For instance, the melting of polar ice during summer reduces the albedo effect, which is the reflectivity of the Earth's surface. Ice and snow reflect a significant amount of sunlight, keeping the planet cooler. When they melt, darker ocean or land is exposed, which absorbs more heat and further accelerates warming. Conversely, the formation of ice during winter increases the albedo, reflecting more sunlight and helping to cool the planet. Human activities have also begun to influence the Earth's climate system. The increase in greenhouse gases such as carbon dioxide and methane due to industrial activities has led to global warming, which is altering seasonal patterns. The timing of seasons is shifting, with spring arriving earlier and winters becoming shorter and milder in many regions. These changes have profound effects on ecosystems and human societies, from disrupting agriculture to affecting water resources and increasing the frequency of extreme weather events. Looking at the broader cosmic context, our understanding of seasons extends beyond Earth. Other planets in the solar system also experience seasons, though they vary significantly depending on their axial tilts, orbits, and atmospheric compositions. For instance, Mars has a similar axial tilt to Earth, resulting in comparable seasonal changes, though its longer orbit means its seasons are nearly twice as long. The gas giants, such as Jupiter and Saturn, have more complex seasonal patterns due to their thick atmospheres and the tilt of their axes. Studying the seasons on other planets provides valuable insights into the dynamics of planetary climates and helps us understand the potential habitability of exoplanets. By observing how seasons manifest in different planetary environments, scientists can refine their models of climate and atmospheric behavior, which is crucial for predicting the conditions on planets orbiting other stars. The interplay of celestial mechanics that give rise to seasons is a testament to the interconnectedness of the cosmos. From the tilt of the Earth's axis and the shape of its orbit to the influence of its rotation and the stabilizing presence of the Moon, these factors combine to create the rhythms of life on our planet. Understanding these processes not only deepens our appreciation for the natural world but also underscores the delicate balance that sustains life on Earth. As we continue to explore and study our solar system and beyond, the knowledge we gain about the seasons and their underlying mechanisms enhances our ability to predict and adapt to changes in our climate. It also informs our search for habitable worlds, guiding us in the quest to find planets that might support life. In the grand tapestry of the universe, the dance of the seasons is a beautiful and intricate part of the story of life on Earth.